Hello again. Well, now that we have discussed what a macroeconomic model is, the first thing we're going to do before delving ourselves into the neoclassical growth model is discussing a simplified version of the model, which is sometimes referred to as the static model. And I'm not only going to use this model, the simpler model, to introduce some of the main concepts regarding households and firms. But the most important takeaway of this part of the course is understanding what equilibrium means and also some of the equilibrium implications. And another thing that I'm going to do is to discuss what are the assumptions we are making in this model and what are the implications of the model, and hence we can try to understand what is the intuition of the model, and also under which situations is this model useful. So again, I just want to highlight that this is a very simplified model, and we're going to start from this and we're going to continue building on it. So again, the first thing we need to consider is setting up what do we mean by household, what do we mean by firms, if there's a government, etc. So let us begin with the households. The objective of the neoclassical growth model, as it will be more clear when we get to it, is try to understand how allocation of labor, consumption, investment is done in the economy, and what drives production, okay? What drives labor movements, what drives investment movements, etc. This first model, the static model that we're going to analyze now, is going to be a simpler version of that, and it's only going to be considering households that want to consume and also need to work. And the decision that the household must do is how much to consume and how much to work, considering that working more is going to generate more income, and therefore more income will allow the household to consume more. So one of the things we're going to be doing in this lecture and in generally in the course is we're going to be assuming that the economy, which we can think of this as a country that we're trying to model, this is a world in which there is a very large number of individuals. Nevertheless, each individual in the economy has exactly the same preferences over consumption and leisure or labor. What do I mean by this? There could be a lot of people in the economy, but all of us have this same uh, way of of evaluating a bundle of consumption and labor. This makes our lives very simple because the fact that we're assuming that every individual has the same preferences, we can pick one of those individuals and actually analyze what would that individual do, and that individual is going to mimic the rest of the individuals. This is usually thought of referred to as the representative agent approach. And throughout all the course, I will be dealing exclusively with this, with a representative agent approach. That means I'm going to assume that the economies that we consider have a lot of people. However, all of the individuals in the economy have the same preferences. In this case, and just for simplicity, I'm going to make a particular assumption that the utility of a consumption and labor bundle is going to be given by this function, where importantly, there's three things that is important. First, notice that consumption, the logarithm is an increasing function. So in this case, the utility of the individual is increasing in consumption, which is a usual assumption. And the second important thing is that as labor increases, the utility as a whole is going to go down. So utility is going to be negatively related with labor. This is an important assumption. We are assuming that people don't like working. And the third thing is this parameter eta, which is going to be positive and is going to capture how much is how the utility of labor in the utility function. Okay. Consumers, as it's implicitly assumed here, but I'm making it more explicitly, are endowed with 1 unit of time. And this unit of time, they can split it between either working or enjoying leisure. Okay. So if L is capturing labor, 1 minus L is going to be capturing leisure. And we can see that the utility function is increasing in leisure because 1 minus L is leisure. So higher leisure is going to make the individual more, more happy. Now, that's the household problem. Okay. I will, in the following slides, I will describe with more detail the household problem. But on the other hand, we have firms. Okay. And again, firms are going to be these entities that will bring to the table the production and the technology of the economy. Similarly to the households, we're going to be assuming that there's a lot of firms in the economy, and all of those firms have the same way of transforming their inputs into consumption or into the final good. Now, in this simple model, we're only going to be worried about labor allocation. So we're going to be assuming that production is only going to be a function of labor. In particularly, and again, this is going to be for simplicity, I'm going to assume that whatever a firm produces, which I'm going to note why, that's going to be a function of labor. And in particular, I'm going to make this following functional assumption, which is called usually the Cobb-Douglas production function. And in particular, this A parameter is sometimes called total factor productivity. And it measures, it is related to how productive is hiring an additional unit of labor. We will talk a little bit more about this in a second. And this parameter alpha will be what we call the labor share. Okay. Right now, it may be not as clear of why it's called the labor share. When we get to the neoclassical growth model, I will be more explicit on why it's called the labor share, and it would become clear. Okay, so these are the two ingredients that are important for the model. I'm going to assume, as I told you in the introduction, that there's not going to be a government. And there's going to be a justification for this, and we will talk about this in this lecture. And on the other hand, in terms of information, which remember is the other important element, I'm going to assume full information. And by that, I mean all the agents know all the things that they need to know in order to make their decisions and everything about the other agent in the economy. So what do I mean by this? Households know I mean, households understand their utility. That means they understand that this is the way they value consumption and leisure. But they also know everything about the firms. That means they understand that the firm's total fractal productivity is given by A, and they understand that the labor share is given by alpha. And similarly, the firms understand how they produce, but they also know how the household values consumption and leisure. Okay. So let's delve into the household problem. Households seek to maximize their utility, and this is going to be subject to a constraint. And the main thing that constrains households is that, remember, they like to consume a lot, but their consumption is limited by their income. Okay. Now, so basically, the expenditures of a household, which are in this model given by consumption, cannot be larger than income. Okay. This is a model in which we're thinking of a, and sorry, I didn't mention this before. The reason why it's called static model is because we're thinking that firms and households will interact in a single time. We can think of this as a year, and after that, the economy will end. Okay, so there's no tomorrow in this model. Therefore, there's no way for households to save anything, right? They will. So we are analyzing an economy in which savings don't exist. Okay. And this is going to be important because in an economy where savings can exist, expenditures could be larger than income, and that would be something that we call debt. But in this model, because there are no savings, you cannot spend more than what you have because no one will borrow you since there's no tomorrow. They know that you can repay. Okay, now let's talk about income. The income of households is going to have two parts. On the one hand, it's going to be given by their work. So households don't like working, but the benefit of working is that they're going to receive a wage for working, and it's going to be increasing their income. So that's what we're going to call labor income. And on the other hand, the households are going to have other sorts of income that we're going to call non-labor income. Now, okay, in the model, that non-labor income will have a specific interpretation, but just for now, you can think of this as, well, households work, but they also own assets. For example, they have stocks, or they own a house. So this is wealth or income that is not related directly to working. You just have it. So that's going to be captured in non-labor income. So as I was saying, households, for each unit of time they work, they're going to receive a wage W, and it's going to be paid by the firms. And hence, the labor income is going to be given by W multiplied by L, how much you work multiplied by how much you earn per unit of time. And additionally, they're going to receive a non-labor income, which we're going to call INL. So the problem that the household solve is the following. And again, here I am following the tradition of intermediate microeconomics on how to write an optimization problem. I'm going to assume that you're familiar with this and also how to solve this. Uh, because again, one of the prerequisites of this course was intermediate micro or basic knowledge about optimization. So the household is going to solve maximizing the utility, and the household can only choose consumption and labor. Okay. So in particular, this means that the household cannot choose neither the wage they're paid nor their non-labor income. So these are things that the household takes as given, or another way of interpreting this is the household understands that they cannot influence these values. They can only choose consumption and labor with the constraint that whatever they consume has to be equal to their income. Another way of writing this would be considering a smaller or equal, uh, but because uh, there's this monotonicity assumption on consumption, both problems will have the same solution. So I will assume it holds with equality. So the expenditures of the household, which is consumption, has to be equal to the labor income plus the non-labor income, which is the total income. Another way of interpreting this is, because I was saying there is no tomorrow, it doesn't make sense for households to leave money on the table. So therefore, it's going to be optimal for households to always spend all their income which is what this constraint is saying. Then, because we are interpreting this C as consumption, there's no negative consumption, so consumption has to be positive or zero. And labor is limited to be between 0 and 1. There's no negative labor. And also, because we're assuming this, households have one unit of time, so labor has to be smaller than 1. So now this is the problem of the household, and what we're going to do now is to try to understand how we solve this problem. The first thing we're going to do is we're going to ignore the negativity and these two constraints. So we're going to assume that they don't exist. Later, we're going to check if the solution that we get when we ignore them satisfies these two constraints. So that's going to be important. So if this is the case, then this is the Lagrangian of the problem. Okay. And as I was saying, so that I'm assuming that you know how to set up a Lagrangian and what is a Lagrangian. So I won't go into that. But okay, this is the utility function, and this is the constraint. We only have one constraint, so therefore we only need one Lagrange multiplier, which I'm calling lambda. Okay. Now we're gonna there's two decision variables, which are consumption and leisure, and sorry, and labor. So we have to write or to derive two first order conditions. Therefore, we need to take the derivative of the Lagrangian with respect to consumption and the derivative of the Lagrangian with respect to labor, sorry. The derivative of the Lagrangian with respect to consumption is going to be 1 over c, which is this derivative. Then the derivative of this with respect to c is 0. And the derivative of this part with respect to c is minus lambda. So in order for this to be optimal, this derivative has to be equal to 0. And the derivative of the Lagrangian with respect to leisure is 0. Then minus eta over 1 minus L. And the derivative of this part with respect to L is plus lambda W. So these are the two derivatives of the household's problem with respect to consumption and leisure. If we manipulate these equations a little bit, we obtained these two first order conditions. Okay, these two first order conditions have three unknowns: c, w, and lambda. So in order to get rid of lambda, which is the Lagrange multiplier, and in general is something that we're not looking for, um, sorry, we're gonna divide these two equations. Actually, I'm gonna divide, if I call 1 and these two, I'm gonna divide 2 over 1. This is a usual optimization trick, because by doing that, the lambdas will cancel and I will get eta over 1 minus L divided by 1 over C equals W. And if I manipulate this, I will get eta C over 1 minus L equals W, okay? Which I have in the following slide. I will actually give you 1 second. So this um, this condition is referred to, sorry, as the intratemporal equation, okay? And this is an equation that relates consumption, labor, and wage. So this is called the intratemporal condition. And what we have on the left-hand side, this is the marginal rate of substitution between consumption and leisure. And this is the wage, okay? So basically, the intertemporal condition says that for a household to be maximizing their utility, their marginal rate of substitution between consumption and labor has to be equal to the wage. Okay? Um, that's the interpretation we give to the intertemporal condition. And I will come back to it in a second. So that's called the intertemporal condition. And we can manipulate this to write it in this way. And this way, I rewrote it in a different way than in the previous slide, just because in here I'm showing how consumption is going to be a function of the wage and labor. Okay, this is going to be important because we're going to be looking for two unknowns, which is labor and consumption. What this is telling us is, well, it's sufficient to find the value of labor. And once we find labor using this equation, I can, if I tell you the value of labor, I can immediately guess what's the value of consumption. So basically, this equation is telling you only need to find one of these two unknowns, which is in our case labor. Okay, and well, as I was already saying, this equation states that the marginal rate of substitution has to be equal to the wage. Now, we're not quite done. And the reason why we're not quite done is because we are looking for the labor and consumption functions, and these, or the optimal labor and consumption, and these can only be a function of prices. In this economy, there's only one price, which is the wage. So I need to find what is the labor, optimal labor as a function of wage, and what is the optimal consumption as a function of wage. So remember that we have a budget constraint. So we have this, okay? And we also have the intertemporal condition, okay? That said that C was that said that C was eta W over 1 minus sorry, multiplied by no, I'm sorry. I'm doing this wrong. Sorry about that. That said that uh, that CT was W times 1 minus L divided by eta. Okay, so this was the intertemporal condition. So these are two equations with two unknowns, C and L. So if we substitute this here, we get that this has to be equal to WL plus the non-labor income. So we have then one equation with two unknowns, with one unknown, that is W and L. Okay, I don't know why this doesn't want to erase, but okay. So if we solve, so in this part, again, is one equation with one unknown, which is L. So we could solve for this, okay? And if we solve for this, if we solve for it, we get this function, okay? This is simplified. Basically, what I did was I multiplied eta to this side, and then I manipulated the equation to get this function. Okay, so I'm not going to delve into those details, but you can please do it and check if this is true. So this is going to be the labor supply function. It's what's called the labor supply. And it's called supply because it's the households, the ones that are supplying labor. And I want you to notice two things about this labor supply. The first thing is that if the wages go up, then this term will go up, which means that this term will decrease. But because there's a negative sign here, that means that all of this term will increase, which means that if the wage go up, the labor supply is going to go up. Another way of interpreting this is this function is such that if firms offer uh, households a higher wage, then households are going to want to work more. Okay. So this is kind of intuitive and it's a nice result of this labor supply. So this labor supply will be increasing in wages. Okay. And on the other hand, this labor supply will be a decreasing function of the non-labor income. Okay. So I just want to show you that because the non-labor income is here, if we increase this term will decrease, which means that this term decreases as well. Okay. And so what this is saying is a higher non-labor income is gonna invite households to work less. Okay. Now, intuitively, this is the reason is the following. The non-labor income, well, remember that households don't like to work. So if households are richer and that wealth is not related to their labor, then they're gonna value more leisure, which means that they're gonna want to work less. If you remember your intermediate microeconomics, this is what's called an income effect. Okay, because leisure is a normal good. So if as you're more wealthier, that means you have a higher non-labor income, that's gonna make leisure more attractive and labor less attractive. So we should expect that richer people should be working less, okay, according to this model. Now, we're not completely done because we need to find consumption, as you remember. But if you consider the budget constraint or the intertemporal condition, you can find consumption. Now, this is not going to be critical for what we're doing. So I'm going to leave this as an exercise for you to do. That means find the consumption function that is exclusively a function of the wages. Okay. So that's the household's problem. The household problem basically is going to be to solve for the labor demand function. And we already solved for that, which is this. So the next step is to solve the firm's problem. Okay. So let's go into that. The firm's problem is going to seek to maximize their profits. Okay. Now profits are going to be given by total revenue minus total costs. Revenue is going to be equal to how much money the firm earns due to the fact that they're selling the good. So revenue usually is the price of each unit that you're selling multiplied by the quantity that you're selling. In this model, because it is simple enough, we can forget about this price. We can normalize it to 1, and we won't lose any of the analysis, so we're going to do that just for simplicity. And the quantity, how much the firm is selling, that's going to be that's going to be equal to how much they're producing, and that's going to be given by the production function. Okay, so in this case, the revenue is going to be P, which is 1 multiplied by the how much they're selling, which is equal to how much they're producing, and that's going to be equal by this. Okay, which again, remember we were assuming that it was of this form. So the revenue of the firm is going to be given by this. And on the other hand, the costs are going to be given by the wage. The only cost that the firm has is labor, because we're assuming that it's only firms only take into account labor to produce. So the firms their cost is going to be given by how much labor they hire multiplied by how much costly it is to hire labor. Okay. Now, this profit maximization problem, which I'm going to describe in a second, is going to lead to a demand for labor, and it's called demand because firms are the ones who need labor in order to produce, as well as an output supply function. And both of these have to be a function of prices. And in this case, there's only one price, which is the wage. So the firm solves the following problem. They want to, oh, okay, they want to maximize profits, which is revenue minus costs. As I already explained, revenue is given by this function, and costs are given by this function. So the difference between these are profits, okay? And the constraint is that n is going to be larger or equal to 0. Now, as I did in the household problem, I'm going to forget about this constraint, and then I need to check that whatever I get satisfies this. So this is going to be very easy because this is a single variable optimization problem. There's no need for a Lagrangian or for anything. We only have to take the derivative of this with respect to n, and that's going to be alpha a n to the alpha minus 1 minus w equals 0. Or if we um, manipulate this, we get that the wage is going to be equal to alpha a n to the alpha minus 1. And because remember, alpha is a number between 0 and 1, this number here is negative. So we can manipulate this to get this. Now, a couple of things. This equation here is the first order condition of the firms. So the firms are going to take the wage as given. That means they understand they cannot influence it. So therefore, if I tell they're going to take this number as a number, not as a thing that they can manipulate. And therefore, because they also know what's the value of alpha and the value of a, they will be able to solve for n. Okay, and that's going to give them the optimal labor that they should demand given the wage. Now, this thing is saying that there's a negative relationship between wages and n because n and w and n is dividing here. So another way of saying this is if I solve for n, I get that n is going to be alpha a divided by w to the 1 over 1 minus alpha. That's in this equation I'm just solving. But notice that as wages go up, firms are going to demand less labor. And the intuition behind this is because wages affect firms' costs. So higher wages are going to imply higher costs. And because the firm wants to maximize profits, they are going to reduce the demand for labor. So firms, one implication of this model is that we should expect firms hiring less labor if the wage increases. Okay. Another another important prediction of this is that as firms are more productive, and remember this is captured by the parameter A, they are going to demand more labor. So another implication of this model is if there's a technology improvement in the economy, we should expect labor to go up. And this is another implication of this model. Okay. Now, this is the labor demand function because it's exclusively a function of the parameters, which are alpha and a, and the prices. There's no other variable involved here. So again, this is the first of the condition. Okay. Now we need to also find, sorry, the output, what's going to be the production, and also what are going to be the profits of the firm given their optimal decision. So if I plug W here, okay, I'm gonna get um 1 second. If I plug W there, I'm gonna get that profits W there are gonna be A and alpha minus W times N. So, but I'm gonna replace W with this. So this is alpha A n to the alpha minus 1. So this whole thing is W multiplied by N. And this is gonna be A n to the alpha minus alpha multiplied by A n to the alpha, because these two things here become n to the alpha. So this becomes 1 minus alpha A n to the alpha. Okay, so this is going to be the firm's profits. Okay, in here there's a slight typo, and I'm sorry about this. I will correct this in the slides. It's not a function of prices, it's a function of labor. Okay, but again, with this equation, I can solve, as I already did, for the optimal labor as a function of prices. So if I give you the wage, you can solve for um, the optimal labor. And once you found the optimal labor, you can plug that here, and that will give you the value of profits. So you don't need to find profits as a function of wages, because you already have labor profits as a function of labor, and you have labor as a function of wages. Okay. So the what's next is to try to understand how firms and households interact. And so until now, what we have is, given the wage, what is the optimal decision of households in terms of um, labor and consumption? And given the wage, what's the optimal decision of firms in terms of labor and production and profits? Now, what we're going to do is, how do these households and firms interact? And for that, we're going to use the notion of equilibrium. However, just to not make this lecture super long, let's take a break and then we can continue.